Let's try and do a test to get the motor velocity constant at other voltages. Now here we'll run into a problem. The PSOC is a digital controller. All microcontrollers today are digital. That means that inside, this thing is basically made up of switches. Each of the pins on the PSOC can either be on or off, but they can't be anything in between. So how could we change the voltage to test the speed of the motor at, say, 4 volts or 3 volts? To explain how we can do this, let's zoom way in and think about what happens when we suddenly turn on a switch to the motor. When we suddenly go from 0 volts to 5 volts, like we did in this last test, the motor does not suddenly go from 0 RPM to 350 RPM because the motor has some inertia. The motor starts moving and it takes some time to get up to speed. When we turn the switch off, the reverse happens. The motor starts to slow down. It doesn't just stop immediately. Actually, when we turn the switch off, the motor slows down slower than it sped up. Now, this time scale here is very fast, generally too fast to see. By eye, the motor appears to just suddenly go at full speed. But suppose that we could turn this switch on and off really fast, so that we turn the switch off before the motor has gotten up to speed. Then we turn it on again before the motor has come to a stop. Then off again, and so on. How fast would the motor spin if we did that? As it turns out, there's an easy way to figure that out. Whatever ratio we use to turn the motor on and off, that is also the ratio of the speed that the motor will spin. For example, suppose we know that the motor will spin 500 RPM if we give it a constant 6 volts. Suppose we also know that the motor will spin at 350 RPM if we give it 3 volts. Now, if we turn a 6 volt signal on and off so that it is on for half the time and off for half the time, the motor will spin at the same speed it would have spun if we had given it a constant 3 volts. The motor will spin at 350 RPM, the speed that it would spin if we were giving it a constant 3 volts. In other words, turning the 6 volt signal on and off so that it's on for half the time is the same thing as giving a steady voltage of half the 6 volts. We can do this for other ratios also. Suppose we want to know how fast the motor will spin if we gave it only 1 volt. We could take our 6 volt signal and turn it on for 1/6 of the time and off for 5/6 of the time, and the motor will behave as if we were giving it a constant, steady 1 volt signal. This method is known as pulse width modulation. We actually used this method previously to control the RC servos, and now we can use the same method in a slightly different way to control the speed of the DC motor. Let's try and do this. Let's go get a PWM block and set up the settings. You can find the PWM block in the Digital menu and then the Functions menu. Click and drag one to the screen. Next, scroll down to the Logic menu, which is also inside of the Digital menu. Find a Logic Low and click and drag one to the screen and wire it to the reset input. Then scroll all the way down to the System menu. Inside the System menu, find the clock. Click and drag one to the screen and wire it to the clock input. This time, we'll leave the clock at its full speed because we want the pulse to turn on and off really fast. Now, to set the other settings, we need to learn a bit of terminology. When we are turning a pulse on and off, this amount of time from when the pulse goes on until it goes on again is called the period. The amount of time that the pulse is on is called the compare value. In our PWM settings, let's set the period to 100. The units on this value is ticks of the timer. We could figure out how much time this corresponds to by using the clock speed like this. Our clock speed is 12 megahertz. That means that the clock ticks 12 million times per second. If we take 1 divided by 12 million seconds per tick, and multiply it by 100 ticks, we get 8.33 microseconds. That's pretty fast. Now, let's set the compare value to 100. That's just an initialization value. We are going to be changing the compare value in our code. Now, let's wire the motor pin to the PWM output. We need to double click on the pin and recheck the HW connection box. Then we can wire it to the PWM output. Also, right now we have two outputs but only one pin. Double click on the PWM and change the mode to only one output. Then click OK. Back in our code, let's start the PWM. Now, let's set up a speed test. In a loop, we will set the compare value, wait, take a position measurement, wait 1 second, take another position measurement, calculate the speed, then stop the motor and show the compare value and the speed on the LCD screen. We'll then wait a while to give us time to write down the value. Then we'll loop back and change the compare value. Here's how we can add this to our code. Up here at the top, create a new variable called compare. Now, in the for loop, I will start by setting compare equal to 0. Compare is what will control the speed of the motor. I want to keep running this loop as long as compare is less than or equal to 100. Then curly brackets are what defines what is inside my while loop. So I start with an opening curly bracket. Now, I don't want to just turn the motor on. I want to set the speed of the motor using the compare value. So I do this by using write compare. And compare is the value of ticks that I want to write to the compare value. Next, we want to wait for a bit. Get a count, wait, get a second count. Now, I do want to turn the motor off, but the way we do that now is by using write compare. And the value I have to write is 100. Remember that this pin is connected to the other end of the motor lead, whereas the first end is connected to power. So if I write the compare value 100, the motor will be completely off. If I write the value 0 to compare, the motor will be completely on. Now I want to print to the screen the compare value, and I also want to see the speed value. I'll do this by changing the position at which we will write the value to 1. That means the next row. So the compare value will be printed to the LCD screen row 0, that is the first row, and the speed will be written to the row number 1, that is the second row. I still need this delay here in order to give me time to write down the value. And then I want to increment the compare value. Let's just test in increments of 10. And then I do a closing curly bracket to end this while loop. Now before we actually run this, we need to add one more thing to the top of this code. We're going to be running the motor in the same direction for a good amount of time during this test. We will reach the maximum value of our ability to count the number of pulses from the encoder. So what we want to do is at the beginning of this loop, we always want to reset the count value to 0. We can do that by writing quad deck 1 set counter 0. That will set a value of 0 to the encoder counter every time before we do this test. Now program the PSOC. After the PSOC is programmed, you can hit the reset button to get the code to start from the beginning again. As the code runs, write down the two numbers that we see here. Let it loop back again to get at least one other set of numbers. This first number is the compare value that we're writing to the PWM. The second number is the speed of the motor in RPM. Let's plot these numbers in Excel. I'll make a column called the compare value. Then I'll make another column called voltage. Then speed 1, speed 2, and I captured 3 speed values. So I'll do speed 1, 2, and 3. Now I'm going to put in the numbers that I wrote down while running this experiment. Okay, first, let's see if we can fill in this voltage column. We know that with a PWM signal, the relationship between the equivalent voltage and the maximum voltage, the voltage of our pulse, is the same as the ratio of the compare value to the period value. But there's a little bit of a catch here, which is that our PWM output is not actually turning the pulse on, it's turning the pulse off. Because we have our motor wired up where one of the leads is connected to power, VDD, and the other lead is connected to the pin. So in our case, when the compare value is 0, the voltage is a steady 5 volts. When the compare value is 10, that means that we're turning the motor off 10% of the time. In other words, our voltage is 90% of the maximum. Similarly, when the compare value is 20, the motor is being turned off 20% of the time, and so it's on 80% of the time. Next, you may notice that there was a little bit of an anomaly that happened here when we did the third speed test at the compare value of 60. Why do we have 0 in the first two speed tests and 85 in the third? This has to do with the difference between static friction and dynamic friction. Static friction is the friction that prevents a thing that is not moving from starting to move. And dynamic friction is the amount of friction that tries to stop something that is already moving. Dynamic friction is always less than static friction. Now, when we put in a compare value of 60 to our motor, this was not enough power to get the motor to start moving, that is, to overcome the static friction in the first two speed tests. But in the third speed test, it was enough to overcome the static friction. And so the motor turned relatively fast in this case because once we got past the static friction, the amount of friction actually dropped and allowed the motor to turn relatively quickly. Let's do two calculations here. Let's calculate the mean of the speed and also the standard deviation. Now, the mean of the speed, of course, tells us the average. That is, we add up the three speeds and divide them by 3. The standard deviation tells us the average amount that the actual value in each of the three tests deviates from the mean. In other words, if we would take the difference between each speed and the mean and then average those differences, that's what the standard deviation is. It's good practice anytime you include the mean to also include the standard deviation in your calculations, because that helps you tell how much spread there is in the data. If the standard deviation is really high, that means the numbers are all spread out. And if the standard deviation is low, the numbers are all grouped tightly together. We can use the standard deviation to quote how confident we are that the speed will be as we quote. For example, we can say that if we would write a compare value of 20, that the speed of the motor will be 259 RPM plus or minus 1 RPM. Now let's try and plot this data. I want to plot the voltage versus the speed, and we'll use the mean speed here. When I make this plot, I'm only going to go down to a compare value of 50. I'm going to leave out the value that we got for 60 because its standard deviation is really high. The very high standard deviation means I'm not really confident that this mean value is accurate. The speed at 60 is 28 RPM plus or minus 49 RPM. That's an excessive amount of error, so I'm not going to include that in my plot. Let's make a scatter plot. The x-axis here is voltage and the y-axis is speed. Note that this looks like a pretty good straight line. That's a good sign. The slope of this line will be our motor's velocity constant. Let's click on the data and then right click and do add trend line. We'll do a linear trend line and then we'll do display equation on chart. From this equation, we can see what the motor velocity constant is by looking at the slope. Since y equals mx plus b, let me make this a little bit bigger maybe so we can see it better. This value, 85, is the slope of our line. That's the RPM per volt value for our motor. This will give us a much more accurate number for the motor velocity constant compared to the value we calculated using only one data point before. Remember when we used only one data point, we had gotten the value of 70 RPM per volt. We're now going to use this much more accurate number, 85 RPM per volt, for our motor's velocity constant. We've now learned a lot about the relationships between voltage and speed for a motor, but we haven't looked very much at the relationships between speed and torque. In the next video, we'll look at that relationship.